thing.
Yeah.
Okay, so today's talk is called Methods for the Identification of Buildings and Areas with High Radon Levels, an exhaustive review. So this is the biggest part of the milestone 20 that we submitted last year with the whole team of the 2.4.1. So first, why do we do this research? So the first thing is that the radon hazard would depend on many natural and anthropic factors, and that implies a strong spatial variability. So there is necessity to for the stakeholders, for the population, for researchers, for the public authorities to identify radon-prone areas and also buildings. So through the literature review, we saw that a lot of approaches were applied and in different contexts so far. And here in this study, we wanted to identify these methods and to assess these methods in terms of performance, to see where they were applied, when they were applied, and for what. So this is really important. So first, the first question that came to us was the definition of high indoor radon levels. So the first question was, when do we qualify a level as a high radon level? And here, the first supposition was to use a threshold, so more than 100, 1000, we don't know. Then we have specific thresholds, such as the reference value, for example, which are different according to the countries. Here I put some examples. And finally, we have the recommendation from the WHO, which is 100 or 300, depending on the countries. So this is a good question because the papers don't use the same threshold to see what is a high indoor radon levels. So what did we do? So this paper aims to provide an exhaustive literature review of the papers tackling the identification of high radon areas and buildings. So here we used the PRISMA methodology. So the PRISMA methodology has been developed a few years ago, and here the aim here is to present to screen all the papers that are containing the keywords that we identified, and then look at all the papers that have been selected and see if they are eligible for the literature review. And past this filter, we will have a bunch of papers that will be included in the literature review. So here, more precisely, for the identification of areas with high radon potential, the first one, what did we do? We looked into big databases, which was Scopus and PubMed, and looked, it was on the 8th of July 2022. And here you can see the different keywords that we used to perform the research. And what is interesting here is to see that according to these keywords on these two databases, we found more than 500 records, which then were filtered to see if there were some duplicates. So we found 83 that were on the two databases. And here you can see that they were all screened. And during the screening period, we are looking if they are far good enough, focusing on the good topic. And here you can see that most of the papers that were excluded because they were not focusing really on radon-related risk. The second reason was that they were only focusing on geology and mining and so on. Here you can find all the reason of exclusion. And finally, in this second part of eligibility, we looked at the whole paper to see if they were really relevant passing this filter. And here we still had like 6 papers that were true general overviews. At the end, it remained 42 papers, and these 42 papers constitutes our core of the literature review. Then we did the same thing for the high radon level in buildings, and here we looked in three databases. Also on the 8th of July, it was Web of Science, Scopus, and PubMed. And here you can still find the different keywords for the research. Here we had a bit less paper, so we recorded at the beginning just a bit more than 300 records. Then during the screening paper, the screening step, we excluded for different reasons, but the same. The first one was because it was not focusing on high radon levels, and the second reason was that because it was not focusing on radon-related risk. And finally, here on the eligibility step, we looked at the papers, and some of them were not focusing again on high radon concentration. Here, the thing is that at the end we only had 10 papers to look at it. So from these papers, we looked at the different methods that we found, and we classified them in 4 main categories. So the first one was the descriptive statistic with the basic aggregates, for example, the means, the ranges, and so on. Some visualization through different kind of plots, the correlation analysis, the variance, and the PCA, the principal component analysis. Then we have the regression class, which is filled by the quantile regression and the logistic regression. Then we have the geostatistics. Lots of papers use geostatistics to assess the indoor radon-prone areas, sorry. So here we have the inverse distant weight, the creating the geographically weighted regression, the local and or the global polynomial interpolation. And finally, since 2010, around 2010, a lot of papers are beginning using the AI methods with 3 big tool here. We have the random forest, the support vector machines, and finally the feed-forward neural networks. So now I'm going to go through all these different methods that I listed here to show you some example of application and in which context they were. And just a word of what I'm going to present right now. So this is not, it's not all the contents that I will present regarding a paper. This does not constitute the whole content of the paper. So it's not a summary of the whole content of the paper. It's sometimes just a part of the analysis, which is in a bigger content. Okay, so let's go for the descriptive methods. So the first one that we highlighted was the correlation analysis, which is has been used in different papers to assess the link between the indoor radon level and the geology, the uranium content, the gamma ray survey, for example, or the radon exhalation rate. And here we do have an example here. It's a pretty old example in 1996, which was a tentative by Kensky and al. to map the radon potential of Germany using a correlation analysis. Then we do have the variance analysis, the ANOVA. Here, it has been used in different papers to look at the relationship between the indoor radon levels and the measurement of the equivalent uranium concentration, the uranium concentration in sediments, but also geology. Then we do have the principal component analysis. So the PCA is a tool to summarize, not to summarize, but to reduce the information of many parameters to different axes, which will be summarizing different parameters. So here it has been used in a very specific context here. It was to look at the factors that were affecting the hydrochemical components and radon levels in groundwaters. So this is an approach that is allowing to predict areas with high radon potential in groundwaters. And then here we have a big class which is the statistic by geographic grouping, and the aim here is for a grid square or for a spatial unit to combine the different statistics and to show that in a map. So here, for example, we have the example of Miles and Appleton, which is showing the radon potential map of Southwest England based on geology and indoor radon measurement. And we can see here, for example, the black units here, the squares in black, represent more than 24% of the indoor radon measurements are above the action level of England in 2005. Then we have the regression methods. So we highlighted two main methods that were applied. We have the quantile regression. So the quantile regression is the simple extension of the classical regression, the multiple regression, but it's going to look at different parts of the distribution of the response variable. So for example, which is very great in this with this method, is that we can look at the 5th percentile of the distribution, but also at the 95th percentile, which is really interesting to look at, because we want to go to high redundant levels. And then we do have the logistic regression. So the logistic regression is a binary predictor. It's going to predict the probability of an event to take place or not to take place. So for example, looking at are we upper the threshold of a high indoor radon level, or are we below? So it's really it's a good tool to look at the different zone. Are we upper or are we below? So here I'm just giving you this paper, Stanley and al., which use the logistic regression to look at the influence of some structural attributes of the buildings on the radon level. So not all the plots here were provided by this method, but in fact, they used the logistic regression as a threshold. Are we upper, are we below, for a defined threshold. Then we do have the geostatistical methods. So the first one, and maybe the most simple to implement, was the inverse distance weight. The IDW is a deterministic tool which relies on existing data measurements. So it means that the closer, if we want to interpolate a surface, at a certain point, the closest measurement point will be more influencing than the more far, the other that are more far away. So here there is only one parameters to fit. This is the power. This is to give to give a ponderation to the influence of the distance points. And then we do have the kriging. So the kriging is another approach than the inverse distance weight, because here we are looking at the existing data, but also at the statistical relation between the existing data measurements. So here the result of a kriging will be an interpolation map, such as the one on the right here, but also it will be linked with an uncertainty map issued from the statistical modeling based on the existing data measurement. So here, the example, this is an interpolation that has been carried out in the Campania region in Italy, and it clearly highlights here high radon levels in the Napoli province, and more specifically to the Napoli city. Then we do have the geographically weighted regression. So this method is an extension of the regression, and this is a tool that allows to predict an indicator according to different variables, and it can include non-stationary variables such as the climate or the geographical coordinates, for example. And for example, here I put here a result that has been applied by Pasculianal in 2014. It's really interesting because we can see here in A, this is the coefficient of the regression, the intercept of the regression. In B, we do have the equivalent uranium concentration. In C, we have the altitude, and in D, we do have the permeability of the soils. And this is really interesting because we can see here different spatial variability of the coefficients, but also of the p-values. Then, and finally, for the geostatistical methods, we do have the local and or the global polynomial interpolation. So this is a two-dimensional interpolation, which is based on a polynomial function. And this is applied as a filter on a part or to the total of the surface. So, for example, if you want to interpolate to the whole territory, it's going to be a global polynomial interpolation. But for just a part, it's going to be a local polynomial function. And if we want to predict a whole territory to interpolate using small pieces like a grid, each grid will be we will create a function, a polynomial function for each grid, which will then give us an interpolation for the whole territory. It has been used here in two papers by Akala, and then in 2013 and Yarabolu in 2013 too. Okay, and now let's speak about the last category, which is the AI methods. So in this category, we looked at the three main methods. The first one is the random forest. So here the random forest consists in an aggregation, of multiple results of different decision trees. So we are carrying on many times these steps, and then based on 1,000, 2,000, depending on the setting of the model, we will use they will be used for a classification setting. And this is really interesting because here we can classify, for example, different class of radon levels, for example. It has been used here by Kopat, and I will show you an example later. Then we do have the support vector machines and the support vector regression. Here, these algorithms were developed for binary classification tasks. So here, this is really the output could be really similar as the logistic regression output, since that it will result in two classes, and here in this method, this is going to be a space which will be separated by a linear boundary. It has been used in Peterman et al. Paper in 2021. And finally, we do have the feed-forward neural network, and here we have an input, an output, and in between these two, we have different layers of neuronas, which will help to predict the output. And here, this has been really used in regression and classification settings. So here I'm just showing you two examples. The first one is the application of artificial neural networks. This is the predicted map of the radon-prone municipalities in Czech Republic for the whole territory. And we can see here, for example, in some areas, we have more than 20% of the buildings, of the houses in the municipality that is above, the reference value of 300 becquerels per cubic meters. And here in Switzerland, something really similar, which is the application of random forest classification, which allows to highlight different categories. Here you can see that some areas like the Jura Mountains here, the Mont Blanc Massif here, and here the Graubünden, which is also in the Alps, but we do have higher radon levels in these areas. That has been carried out by the random forest tool. Okay, so now this literary review showed us that there is a lot of different application, a lot of models that were showed to predict, for example, average radon level, but also high radon levels. But there is a difficulty to compare all these publications together and their respective results. So, and this for different reasons. So the first one is the database. In fact, all these papers are relying to another database. There is for each paper there is a different database, so it's always difficult to compare things from different database. Then there is the data manipulation. In order to compute these models, to use these models, we have to prepare the data, and the data manipulation. For example, some papers use the average to predict something, and then some other papers used the median. And here we don't have all this information, and it could create a bias here. Then finally, we have the different models. the different models, for example, the kriging, there is different parameters inside the kriging, and some authors could set the parameters to such a way to have a result, and then other authors could use other settings. So it creates also a difficulty to compare, to cross-compare the different publications. And then we didn't find a lot of paper that are evaluate the different models. So here, this is basically the next step of our research in the task 2.4.1. This is to test the method that I showed just before, but on our own dataset, to see on a common database with a common manipulation with models that we will manipulate together. Will we have the same results? And this is really interesting to see for the next step, to see if these models, when we assess them, when we compare them, do we have the same performances? So here, just to go a bit deeper, we retrieved the strengths and the weaknesses which were revealed by the article authors, but also by us and for each method. So here, I'm not going to go through all the different methods, but just to say first that the descriptive statistic method basically are easy to implement. They provide an information which is accessible to everyone, and it's sometimes really easy to interpret. We just found two different weaknesses that can be called the weaknesses, but in fact, when we want to look at an ANOVA, for example, it is mandatory to be sure that we are working on normal distribution, and sometimes it's not the case. Here, for a second weaknesses here is regarding the PCA. When we are carrying out the PCA, there is an interpretation regarding the axis that we find. An author could interpret in a way an axe and another one just slightly differently, which creates, for example, a small bias. Then regarding the regression methods, again, these methods are really not really easy, but they are not the most difficult to implement. They allows both of these methods allow to integrate different indicators, which is a good way to provide the complete pictures of the relationship between all the variables. And one thing we can say regarding this is for the quantile regression, sometimes it's work better when we don't have too many covariates. And for the logistic regression, since it's a binary index, if we want to look at different thresholds, we need to carry out the analysis again. So in terms of time, it may not be the most efficiently method, but it still remains a good method here. For the geostatistical method, this is some tools that provide an interpolation, and here basically they all require a prior knowledge regarding the data set we are willing to apply the method. So for example here, for the inverse distance weight, it will comply very well with the noisy datasets. But for example, the global polynomial interpolation will provide something which will be more for long-range trends. So there will be a difference. Having prior knowledge regarding the data set could be useful to select the good tool to implement. And as a weaknesses here, I would just say that this method, the kriging, may be difficult to implement, since there is a lot of parameters inside to set, and it may be sometimes really difficult to have something really reliable. But in fact, it still remains one of the most used and the best linear unbiased spatial predictor. Finally, for the AI methods, basically they are providing the most powerful predictive models that one can use, but in fact sometimes they remain a bit difficult to interpret since, for example, the neural networks, they are providing a black box, and to interpret them, that can be really challenging. So now I'm just gonna give a word regarding the research perspectives of our work. So it's really interesting to see which predictors, according to the different methods that we have, will have the most impact regarding the identification of the building and areas with the high radon levels. And in fact, this is really related to this. Each model that will apply, we need to look at the sensitivity and the specificity of the model to see if there is a parameter which is more influencing than another. And just a word regarding the, the, the distribution of radon level across a data set, but in fact, in a data set, hopefully, we don't have too many samples with high radon levels. Most of the radon, the indoor radon levels are really low, and we need to take care to do a good trade-off between the weighting of the importance of high target values that we want to show and the model. And this is really, really, really important here to have this trade-off down. And finally, we should have a look at performance evaluation, such as the loss function, which is better suited for the prediction of high values, and if it can be used for different methods, for example, the quantile regression. So I would like to thank you for your attention, and thank you also to the team for letting me presenting this result. I would be glad to answer your question with Sarah and Sebastian. Thank you again.